Okay, now that we've analyzed the original function and the first derivative of the function, we're going to move on to part C, which is determining the intervals of concave up, concave down, and finding any inflection points. So to do this, we need to analyze the second derivative, so I just wrote a little note over here to remind myself. My original function was x squared plus 1 over x squared minus 1. The derivative after we used the quotient rule and simplified was negative 4x all over x squared minus 1 quantity squared. So if we want to find the second derivative of this function, we're going to have to use the quotient rule yet again. Remember, the quotient rule is the bottom, which is x squared minus 1 squared, times the derivative of the top. Well, the derivative of negative 4x is negative 4, minus the top, so that would be minus negative 4x, times the derivative of the bottom. Here we're going to have to use the chain rule. Bring down the power of 2, keep the inside exactly the same, so that's x squared minus 1, to the power minus 1, so that would be to the first power, but never forget, with chain rule, you have to take the derivative of the inside. The derivative of x squared minus 1 is 2x. All of this is over x squared minus 1 squared, but then we need to square that, so that it's really going to be x squared minus 1 to the fourth. So in simplifying this, what's easiest to do is look for anything that you can take out in common up top right away. So for instance, I see a negative 4 is certainly in common with both of them, and both of them do have one of the x squareds minus 1 in commons as well. So if on top I want to pull out anything in common, I'm going to pull out that negative 4. I'm also going to pull out that x squared minus 1. Give me 1 second. So negative 4 and then an x squared minus 1. I'm going to think about what would be left in that first term. Well, I took away the negative 4. I took away one of the x squared minus 1s. So there'd still be an x squared minus 1 left over. Let's look at that second term. Well, I have a minus. I took away the negative 4, so I still have an x. I have a 2. I took away the x squared minus 1, and I still have a 2x. So it seems like we have a 2x times a 2x, which would be a 4x squared is left over in the second term. And all of this was over x squared minus 1 raised to the fourth power. X squared minus 1 is now a common factor on top and on bottom. So on bottom, I'd now have x squared minus 1 to the third power. On top, I'm going to go ahead and distribute or combine like terms so that x squared minus 4x squared is going to be a negative 3x squared. And let's see what we end up with. I'm ending up with, on top, so here's my second derivative. On top, I have a negative 4 times what will be a negative 3x squared minus 1. And on bottom, I have an x squared minus 1 quantity cubed. Again, we want to find our possible inflection points, so I'm going to look, when is that second derivative equal to 0? And when is that second derivative undefined? So again, a fraction is equal to 0 when its numerator equals 0, so I'd have negative 4 times negative 3x squared minus 1 equal to 0. Divide both sides by negative 4. I'd have negative 3x squared minus 1 still equals 0 because 0 divided by negative 4 is 0. Add 1 to both sides, so I'd have a negative 3x squared equals a positive 1. Divide both sides by negative 3, I'd have x squared equals negative 1/3. I know that can't happen because you can't square a number and get a negative, so there are no points where the second derivative is equal to 0. Let's look now, when is that second derivative undefined? Well, anytime a fraction, the denominator of a fraction equals 0, it's undefined. So in this case, it's x squared minus 1 quantity cubed equal to 0. Take the cube root of both sides, you'd have x squared minus 1 equals 0. Add 1 to both sides, we'd have x squared equals 1. I'm going to take the square root of both sides, remembering plus and minus, so I'd have x equals negative 1 and 1. Again, we would say those are our possible IPs, but if you go back to step A, we realize that x equals negative 1 and x equals 1 were our vertical asymptotes. So that means our function is not defined there, meaning those cannot be inflection points. We still need to determine intervals of concavity, though. So let's do what we always do. Let's create that number line. Let's plot these points of a negative 1 and a 1. I'm thinking about the second derivative, the value of the second derivative during all these points. At negative 1, it was undefined, and at 1, it was undefined. My first interval is negative infinity to negative 1. Second interval is negative 1 to 1. And last interval is 1 to infinity. I'm trying to find out what happens to my original function given those. Let's go into our sign chart now. Here's our x values. We're plugging it into the second derivative. which was negative 4 times negative 3x squared minus 1 all over x squared minus 1 quantity cubed. I can give this a little thought. I know x squared is always positive, so negative 3 times x squared is always going to be negative, minus 1 is negative, times negative 4 has to be positive. So truly, no matter what I pick for the numerator, I know that my numerator is always going to be positive. That's not the case with the denominator because it's raised to a third power, so I don't know it is, so I do need to test these intervals. So I'm just going to pick some test points about negative 10, 0, and 10 for the first, second, and third interval. If I plugged in a negative 10 just analyzing the denominator, I'd have 100 minus 1 cubed, which would be a positive number. A positive over a positive is positive, so my first interval has to be positive. Let's go to that second interval. How about 0? I'd have 0 squared minus 1, which is negative 1 cubed, which would be negative. A positive divided by a negative is negative, so that entire middle interval is negative. I plug in 10, again I'd have 10 squared, which is 100 minus 1, it's 99 cubed, which would be positive, and a positive over a positive is positive, so that entire last interval must be positive. So it seems that because my second derivative is positive on the first interval, it must be concave up. Second derivative is negative on the second interval, concave down. Second derivative positive on the third interval means it's concave up. You would want to say that negative 1 and 1 are inflection points, but again, these are not inflection points because my function is undefined. These are vertical asymptotes, but that's a common mistake made on the test, is they would say because these change concavity, they're inflection points. Again, if it's a point, you'd have to try plugging negative 1 into the original function. That's where you would have caught that it was undefined and known that there were no inflection points. Okay, so what were my intervals of concave up? Where the second derivative was positive was negative infinity to negative 1. We also had the interval 1 to infinity. Where was it concave down? Was on that middle interval, negative 1 to 1. Okay, so that gives us all our information from our second derivative with the concavity. Now we want to take all the information from parts A, B, and C, that we've done so far, put them together, and create a rough sketch of this. So let's go ahead and go back to part A and see what kind of information did we get. Well, we got the first information that we do have a y-intercept at 0, negative 1, so I'll plot a little point there. We know we have a vertical asymptote at x equals negative 1, so let me go ahead and drop that down pretty far so I can get this information. So this is x equals negative 1. We also have a vertical asymptote at x equals 1. Okay, and then we have a horizontal asymptote at y equals 1. So I'll draw a horizontal asymptote here. Notice I am labeling the equation of the lines for all of my asymptotes, and I'm putting dotted lines for them. That's what I would expect if you were to graph these by hand on the test. Okay, so that looks like all the information from step A. Let's go on to step B. I know that the point 0, 1 is a maximum, so I'm going to write that right there for myself. It's a maximum. I know I broke it up at negative 1, 0, and 1, so I need to draw a little dotted line at x equals 0 because I've already broken it up at 1 and negative 1 from the vertical asymptotes. I know there is no minimum, so let's just go in and write our sign of the derivative for each one of these intervals. From negative infinity to negative 1, it was positive. From negative 1 to 0, it was also positive. It was undefined, of course, at the vertical asymptote. At 0, it was 0, which we knew was a maximum. We've already plotted that. And then we know that it was negative from 0 to 1, undefined when x equals 1 because of the vertical asymptote, and then negative from there on out. So that's all the information that we had from part A and part B. Let's move on to part C, which was concavity. Not much to do here because there were no inflection points, but we can write down where we broke it up. We broke it up at negative 1 and 1, which we've already broken it up at, so that's nice and easy. Let's remember our signs of this. So it seemed that our signs for the first part were positive all the way up to negative 1. In between negative 1 and 1, it was negative. And then after 1, from 1 to infinity, it was back to positive. Why do we care about that? Because if we know the sign of the first derivative and the second derivative, we're able to determine the exact shape of the graph. So let's think about this. Let's put it together. My second derivative positive means I need to be concave up. And my first derivative positive means I need to be increasing. So I'm a smiley face, and which of the smiley faces going up? It looks like I have to be the right half of a smiley face. I have to be the right half of a smiley face. Well, I have to come in here and I have to look at this, and I'm going to use the little laser pointer. I know that my function has to approach both the vertical and the horizontal asymptote. So here it seems what I'm going to have to do is as x approaches negative infinity, I need to approach the horizontal asymptote y equals 1 from the top. And then as I come to the right and I come to x equals negative 1, as I approach x equals negative 1 from the left, my y values need to go up and approach infinity. So that would be the way to get the right hand side of the smiley face in that given information with those given horizontal and vertical asymptotes. Let's go in the next little section. I know that my second derivative, this is from negative 1 to 0. My second derivative is negative, so it has to be concave down. My first derivative is positive, which means that I have to be the left side of a frown face, the left side of a frown face. So again, I need to approach that vertical asymptote. So I know as x approaches negative 1 from the right, I need to go to negative infinity. And then I'm just going to draw that left half of a frown face all the way to the point 0, negative 1. Going to the next interval, 0 to 1, my second derivative is negative, so I have to be concave down. My first derivative is negative, so I have to be decreasing. So it seems to me that I have to be the right half of a frowny face. Nice and easy, I connect from the point 0, 1, and I go down, approach that vertical asymptote of x equals 1. So as x approaches 1 from the left, my y value approaches negative infinity. Let's go to that last interval. Again, my second derivative is positive, so I have to be a smiley face. My first derivative is negative, so I have to be decreasing, which means I am the left portion of a smiley face. Again, I have to approach both the vertical and horizontal asymptotes, so this tells me I have to be in that upper quadrant area, where as I approach 1 from the right, I have to approach infinity, and as x approaches infinity, I have to approach y equals 1 from the top. So we have the point 0, negative 1 being our max. We have no x-intercepts, no other y-intercepts. Everything looks great to me here. So this is where I go to Desmos, and I would check on Desmos. Is this what the graph actually looks like? Again, we're not caring about the exact x and y values here. Well, x values we are, but y values not really to scale. It's not such a great picture. But what I care about more so is the behavior and the shape of the graph, which we've shown everything in this window.